I'm going to talk about how one of the blocks from a single parachain makes it all the way to finalization, and it goes through like a lot of checks. And like a lot of sharded systems do this. So like Jack mentioned that Polkadot is a sharded system. And this like the way that we actually have, the way that we guarantee availability and validity with 10 validators per parachain, as opposed to like Ethereum that will have like 1,000 validators per shard. That's really like all comes down to the way that we provide these availability and validity guarantees. And it's like the really like unique thing that Polkadot does. So I was just saying I will answer your questions, but it'll be a much better answer at the end of the talk. So if I forget, then remind me. So yeah, Jack already showed you this. We have this relay chain validators, parachain collators, and more of them. Okay, so yeah, so Jack mentioned that like they're heterogeneous shards, but it really depends on like which side you're looking at it from. If you're looking at it from the parachains, they're heterogeneous because they each have their own state transition function. But if you're looking at it from the side of the relay chain or the validators, it's actually homogeneous because the Polkadot relay chain client has a WASM compiler and an interpreter in it, and the main rule of your parachain is that you have to be able to compile your state transition function to WebAssembly. And what Substrate does is it basically like takes your whole state transition function and it compiles it all down to a single function that's called execute block. And each parachain presents this execute block function to the relay chain. And so this execute block function, whatever is behind it, is completely abstract. Like the relay chain doesn't know about it. It's just this function that says execute block. So from that point of view, every parachain looks the same. So they're homogeneous shards from the point of view of the relay chain. But since the logic is abstract and every parachain can put whatever it wants behind that execute block, each shard can be different. So you have this network of parachains. Each one has its own state. So like the really simple example, A equals 4, B equals 0, and then you have this block, which is a batch of state transitions, and one of them might be sent to from A to B, and then you have a new state that says A is 2 and B is 2. So the thing here is that they share state and validation logic with the relay chain. So they're sharing this validation logic through this execute block function. And they're sharing state because, we're gonna talk about this later, but like so the parachains are all following the relay chain because they have to for finality. They have to like know which chain to extend. But the thing that makes Polkadot sharded that like other like bridge solutions are not is that the relay chain is also following the parachains as a light client. So it has all of like the header data and state roots in the relay chain. And so that's basically like how these shards are sharing states is that in order to roll back a single shard, you have to roll back all of Polkadot because all of this, all of these state roots are in the relay chain. So we're going to start with like how like one of these blocks from a parachain makes it all the way to the relay chain. It's kind of a long journey, but it starts with the collators. So collators are running full nodes on their own parachain, and so like part of this Cumulus client is that you're running a full node on your parachain and a light client on the relay chain, so you kind of know like what the latest finalized block is from the relay chain. And so each parachain can decide how it chooses its collators. And so this is kind of important in consensus. If you're familiar with Polkadot's consensus, we separate the block production from finality. So if you think of like proof of work, the proof of work part is really just like how you assign the right to produce the next block. The actual consensus rules of Bitcoin is like which chain do you extend, which chain is like the Bitcoin chain. And so you could use proof of work in a parachain to decide which collator is allowed to submit the next block, but they're following the finality of the relay chain. So you could have proof of work, proof of stake, proof of authority, you could have a tokenless parachain, you could do whatever you want. You could have one collator if you want. There's no like security penalty to that. It's all of the securities coming from the relay chain. And so like however you select your collators, it's not really like consensus critical. You just need to have one so that you can submit blocks to the relay chain. So Yeah, so like Jack said, these validators kind of like move around and we shuffle them every time. So one problem if you have like only 10 validators per parachain is that if they just stayed there, they could kind of like get to know each other and start to like, hey, let's try to like make some extra money for ourselves. So we actually like shuffle this every single block. So every single block, all of the validators get reshuffled around to the different parachains. Yeah. So don't ask me how they find each other.
Okay, I wasn't, so we're on the same page. Like, what kind of attack might colluding, like if you didn't do this shuffling thing and it's like always the same 10 validators on this particular parachain, like what kind of nefarious thing might they do?
Yeah,
fixed prices with the cost.
So there's no like, this doesn't know anything about prices.
Okay.
There's like, prices are kind of like outside the chain, it's like kind of what people decide to do. So you're gonna see like at the end, there's not really much that like the validators could do besides censorship. So like, there's kind of like there's two attacks that could go on with like on a parachain level. One is like you try to double spend or like roll back, like reorg the chain, which involves rolling back and reorganizing all of Polkadot. So like, you can kind of say like, hopefully that's not gonna happen. The thing where like validators could get involved in an attack is just censorship. If like the collators decide like, hey, we're not gonna allow transactions from these addresses, and they kind of get the validators to agree, like even if some collators don't participate in the censorship, and submit transactions from these addresses, then they could kind of collude with these validators to just reject those blocks. But as far as like invalid blocks, there's really nothing those colluding validators could do. So yeah, then my next point, that they establish connections, that's still, there's like kind of two ways you can do this. One is that you can have the validators, they get assigned to a parachain, and then they have to go like find that parachain. And the other way, you can do it like the other way around, where like the parachains have to find the validators. And so like the parachain collators have access to the DHT of the relay chain, so like they can do that. But the other way to do that would be to kind of have like boot nodes for your parachain and just say like, hey, when the validator gets assigned to parachain 7, these are some like kind of like entry nodes that you can go in to find other collators there. We just haven't decided which of those we're going to do yet. And so you have you've selected your collator that's going to, so every single relay chain block, which is 6 seconds, these parachains get to make a block, and through your proof of stake or work or whatever, you've decided which one of them gets to do that. And they're going to send this big piece of information called a proof of validity to the validators. So very quick, like what a parachain state might look like. Most people here are familiar with like a Merkle tree. Anybody not? No? Okay. Yes, you are. Okay, everybody's good with this. You have like a bunch of state entries, they all get hashed, and then they just get hashed again and again and again until you get to a state root. So a proof of validity is basically like the old state roots plus a block, and then plus the new tree, but it's pruned. You only have to have like the entries that have been updated. So like in this example, I just took like the last one, and I just changed like the free balance of Ben and Louise and added a referendum. So you could say like a few things happened here, and then but the other nodes in this tree, they don't need to be updated, so you can just store the hash. And of course, like the hash is just 32 bytes. So these storage entries that are unchanged, they could be like an arbitrary size, and you don't need to pass this information. You're only passing 32 bytes, like no matter how big the entry is. Yeah, Joshi.
So this is I think a good diagram. I want to make sure I'm getting it right because I haven't really ever understood what like these proof of validity ones were. So like on the previous slide, you have the whole state and all the data, and all the data.
That's a full node.
Okay, yeah. So like that would be like what the collators have, I guess.
Yeah.
Okay, and so all the data is on the bottom, and you build this tree on top, and then like whatever you're doing in this block doesn't need to change every single one of those things at the bottom. I guess like it just needs to change 3. Is that the idea here?
Yeah.
So you like didn't have to include all those nodes. You only included the ones you showed here.
Yeah, and like so since you have the old state roots, you can just calculate the new hash leaves and then take the old hash leaves, but without the actual like pre-image behind them, and you can compute the new state root and verify that like this is actually a valid state transition without like having the full state tree, only like the updated part and then like the free leaves.
Cool.
Yeah, so obviously the actual state tree is like much bigger, there's more than 8 things in there, but yeah, you get the idea. So there's a proof of validity. So every parachain is going to make one, I don't remember what, so it's back. So every parachain is going to make one of these and submit it to the validators. And so you have like 10 validators who are on this parachain, on each parachain, and they're gonna just like gossip this amongst themselves. So you're gonna have like 10 validators, and they're gonna pass this thing around, and they're going to validate it. And once more than half of them agree that this is okay, then it's gonna move on to the next step. So I'm just gonna like kind of recap here because like we've been focusing on a single parachain. But yeah, so we have like, let's say we have like 1,000 validators and 100 parachains. It's gonna be 10 validators per parachain. Every parachain submitted this proof of validity, which is like a pretty huge amount of information. I mean, relative to like a single, if you have 100 parachains, we don't want to put 100 times of this into a single block because that's just going like, it's the block plus extra, so doesn't really, not practical. And then like the 10 validators in that group are like kind of gossiping around. So like all of this is happening in parallel on like each parachain is doing this. And then like once more than half of the validators on the parachain agree that it's valid, they start preparing the next step. And that is to get it to the relay chain. So yeah, the POV is like pretty big and we want something that's like constant size. And so what I mean by that is we want, no matter how big that POV is, so like let's say that a parachain did a runtime upgrade where it just like completely wiped out its runtime and uploaded a new, like called like the set code function, and it has a new runtime, which could be well over a megabyte, and or you could have a block that's just like a few hundred kilobytes, and we want whatever goes with the relay chain to be the same size, no matter how big the information is that happened on the parachain. We want to always be able to represent it with the same thing. Yeah.
You like the exact same size, or like like no bigger than a fixed size?
It should always be the same size. I mean, as small as possible.
Okay.
Yeah.
Right, yeah.
Yeah, but you don't want like a bigger POV to lead to a bigger candidate receipt that's going in the relay chain.
Yeah. Okay.
Yeah. So we prepare those candidate receipts, which is a really long list of information, but they're all constant, they're all the same size. So like a parachain ID is be like a U16, a collator ID and signature is like a fixed size. The parent block's candidate receipt, like a hash of that, 32 bytes. A couple Merkle roots, also 32 bytes. Hash of the block, 32 bytes. You see where this is going, more state roots, all 32 bytes. And so now the collators have to prepare this thing, and so ends up being, I can't multiply this off the top of my head right now, but 100 or 200 bytes that goes into the relay chain. So this is like what actually is going to go into the relay chain. And the only thing here that might be confusing is the erasure coding. And the outgoing messages. I'm going to answer your question now. This is a good point to do that. Yeah, so like I just said, like no matter what happens on these parachains, we want what's going in the relay chain to be the same size. So if a parachain sends 0 messages or 100 messages, we don't want that to affect the relay chain. So they're going to take these messages and make their own little like kind of like Merkle tree out of it. So instead of like storage items, these would be messages, and they would just get like a root of their messages that they've sent going. So none of these messages are going to go through the relay chain. So at this point, if 2 parachains share full nodes, they can just put this message root into the relay chain, and they can just have the full node send the message for them. Or if they don't share full nodes, they can just go to the validators, send the message to the validators, and the validators will get it to the destination chain. But they don't actually have to like send the message through the relay chain. So it's kind of like the relay chain, you can't just like randomly send messages around to people and like spam them. You have to open a channel with them. So like if we wanted to talk, I'd have to like send you a request like I want to open a channel. and then you would have to send a response of like, okay, like I accept this connection, and then we can send messages to each other. So like that opening transaction goes on the relay chain, but then our messages aren't going on the relay chain, we're just passing them directly back and forth. Does that answer your question?
Yes.
All right, cool. So yeah, most of this should be pretty clear. Is there anything not clear besides the erasure coding? Now's a good time to stop for questions.
So when you explain the erasure coding, is that gonna answer the question of like, well, we still have to send, like, if there happen to be a lot of messages on this parachain, like, we still need to send them up there, I guess, right? Or do the validators really never know, how do they execute the block without knowing all of that data that's potentially bigger than O of 1?
They've already, like, so the validator, we're still in like Parachain land of like only 10 validators, like this hasn't gone out to the rest of Polkadot yet.
Okay, right.
So like they got the like the previous state root and the modified state tree and the block. So that's all they need to validate that this is like a proper block.
But that stuff that you just listed, that's not constant size, right? That the block is, however, okay, that's not the
Yeah.
part that you're saying is.
But that's not going to go in the relay chain. It's just like the hash of the block and then the rest of this.
Oh, okay.
Yeah.
So the full set of information that can be really big gets sent to these 10 specific validators that are assigned to the parachain. They do the full execution, and then.
And then they're preparing this candidate receipt.
Yeah. Oh,
Yeah.
that's what you described here, which is that thing's fixed size, but
Yes.
yeah. So all the rest of the validators on the relay chain are only going to see this smaller thing.
And a little bit of the erasure coding.
Oh yeah. Okay.
But we'll get to that. So, but this is the only thing that's actually going to go into a relay chain block.
Okay.
Is this?
Okay.
It's just like a concatenated list of hashes.
Okay.
It's like a VEC of hashes. So
Yeah.
this is fixed size, and this represents like the whole POE.
Got it.
Yeah. Okay. So the erasure coding. This is super boring, even to me. But so we're gonna take this like POV block and we're gonna make an erasure coding, which there's like no good visual way to do this, but an erasure coding is you take some message and you break it into a bunch of smaller messages such that some fraction of those messages can reconstruct the original message. And so you can configure this however you want to. So like you could make it so that like 1/10 of the messages can reconstruct the original message. But the way we do it in Polkadot is that you need 1/3, which just goes along with like you need to have at least 2/3 of the validator set. That's not malicious. So we say at least 1/3 is needed to reconstruct this. So we take the POV block and we break it into chunks. And then like these messages in erasure coding are called chunks. And we send them out to every validator. So if we have 1,000 validators in the system, we're going to make 1,000 chunks, and you would need 334 of them to be able to reconstruct the POV block. And then we create another Merkle tree with the chunks as the leaf, and we get the Merkle root of the this just die.
Oh, I can hear you perfect.
Okay.
Yeah.
I don't know if it needs to reflect the video. Anyway, so then we take the Merkle root of that tree and we put it into the candidate receipt. So that's this thing, 1, 2, 3, 4, like the fourth one, the erasure coding. So we're gonna take the Merkle root of that, and then we're going to gossip this out to the network. So, well, the candidate receipt gets gossiped, the chunks are kind of like going more directly. So you're going to have you're just gonna send this like candidate receipt out to like everybody, and like the validators are gonna get it and gossip it. So it's like, I'm just gonna, if I receive a candidate receipt, I'm just gonna like start sending it to everybody I'm connected to, and then you have unique chunks to each validator. So like you're gonna start sending out like one chunk of this erasure coding to all the validators, and then yeah. So now everybody in the network should have like this candidate receipt in their transaction queue and some part of an erasure coding. So like 1/1000th of this POV block. And now we need to make a block because we actually have one of these candidate receipts in our transaction queue, and that means we can start putting them into blocks. So yeah, so like Polkadot has its own block construction or like block authorship algorithm called Babe. probably going to be changed to something called sassafras, which is also super cool, but we don't have time to talk about it. So when one of the relay chain validators, when it's their turn to make a block, they have to decide like, well, hey, I have this huge pool of candidate receipts. Which ones am I going to put into this block, right? So the main two rules are that whatever candidate receipts you put into a relay chain block, you have to have already a parent candidate receipt in a parent relay chain block. So you have to actually be extending a chain that's going to the relay chain, and then you have to have your corresponding chunk of the erasure coding for this thing. And so it is possible that you could have a candidate receipt, but you haven't gotten your chunk yet, because the chunks are going out to specific validators, but the candidate receipts are being gossiped, so somebody might have sent you their candidate receipts, but you haven't gotten your chunk yet. So you're just not going to build a block with that. And then we have this availability grace period where if this sits around for a while, if it's been 10 blocks and you still don't have your erasure coding chunk, then you send out a kind of notice to people hey, I haven't gotten my thing yet. So and then if enough validators kind of raise their flag and say I never got an erasure coding chunk for this, they just throw away that candidate receipt and it's gone. So now one of these candidate receipts are actually in a relay chain block, and now it has to get finalized, but we're not quite there yet. There's still more to do. So yeah, they have to actually like save these candidate receipts. They have to save their erasure coding, and we need to make sure that the blocks are actually valid, because since we only have 10 validators per parachain, we still don't like really trust them. So we want to make sure a little bit more. So now the collators come back. We've been in like validator land a little bit. So the first thing is that the collators are going to start like asking for these chunks back. So like they're going to see, hey, my candidate receipt is in like some unfinalized block on the relay chain, and I want to make sure that it's actually available and like these validators have saved their erasure coding. So actually like what's more exciting than the erasure coding is like the reason this would be a problem. And so imagine that like you had a malicious collator, and this collator just like comes online and it's its turn to build a block, and it submits this POV block to the validators, and it just like immediately like unplugs, goes offline, it's gone, and then this block is finalized. Well, now this parachain is like really shit out of luck, because it has a finalized block and it has a new state root, but it doesn't actually have the set of state transitions to get to this new state. That's the pre-image to this state root. So it can't produce the next valid block of state transitions. So like this parachain is stuck, and it doesn't even know how to get to where it is stuck. So if you're a collator, you want to make sure that you can get your block back and be able to reconstruct this and re-execute it before it gets finalized. So once this is in an unfinalized section of the chain, collators are going to start asking for their chunks back. And if they can't get them back, they're going to report this block as unavailable. And then similarly, we don't want to just make sure the block is available. We want to make sure that these 10 validators didn't collude and report something that's invalid. So fishermen who are on the parachain are going to start executing that block and make sure that's valid. If it's not valid, they're going to report that. And at this point, like, what's the next slide? Yeah. We'll get there in a second, what happens if it's invalid. But you can kind of see here that like collators are in a pretty good position to be fishermen. Like they're already asking for this block back. They might as well execute it and check if it's valid as well. But they don't have to. You could have fishermen who aren't collators, and you could have collators who aren't fishermen. Collators don't need to have a stake of dots because they don't really have anything to do with dots, but fishermen do, because like if you claim something is invalid and it's actually valid, then we have to be able to slash you for that. So now we're going to start doing some secondary checks. So like the collators and fishermen can send alerts, but it's still like up to the validators to like guarantee the finality of this chain and the validity of it. So we just randomly select more validators to like construct and execute these blocks. So we just like, not the 10 that were on a parachain, we just like randomly select some validators around Polkadot and say, hey, ask for the erasure coding of this block, reconstruct it, and validate it. And then after we get enough of these secondary checks, then you can actually vote on this block in Grandpa to finalize it. And so we need more than 13 secondary checks, but that number is like, it's dynamic with the reports. So like if people start reporting something as invalid, it'll require more checks. And so, so anything up to like, this can go all the way up to like 1/3 of the validator set. So like if more than 1/3 of the validator set agrees that some block is valid or invalid, then it's valid or invalid. So yeah, we require like more than 14 checks. If you're just like randomly sampling validators, then the chance that like 14 people will incorrectly, or I guess not even incorrectly, it's like maliciously report a block as being valid when it's actually invalid. It would take like 50 years for that to happen, just from probability. So that gives us like, on the relay chain, it gives us like kind of 3 zones. You have this like phishing zone where like people are asking for these erasure codings and chunks, and actually like validating the stuff. And then once it's passed enough secondary checks, then the validators can actually vote on these blocks to be final. And then after it has like the 2/3 in the pre-commit round, then it becomes finalized. So the relay chain has like these 3 zones. And then some more fun stuff. This is the last one. We're almost done. So like some of the like principles about this, it's all about like pushing information to the edges to scale. So like we don't want to be putting more information into the relay chain as the system grows. Like we want to be able to add more parachains without making the relay chain a bottleneck. So number 1, not putting block production on the critical path for finality. So some other not to be named algorithms can only do 1 block at a time, where they like produce this block, validate it, finalize it, and then they move on to the next block. So by separating the block production and the finality, we can like have this section of the chain that's not been finalized yet. So this one's good. Collators and fishermen will increase with the number of parachains. So like these are not on the relay chain. The collators and fishermen on the parachain. So like we need these people to go do these availability and validity checks, but they exist on the parachains, on the relay chain. So if we double the number of parachains, it's not like any increase of burden at all on the relay chain. It's just these things kind of come with the parachains. The cross-chain message passing, we talked about this a little bit. All the messages are going outside the relay chain. Only like the message routes are going to the candidate receipts. And then the fun one is the hermit relay chain, where we just basically make Polkadot a parachain itself. So like we have all this like dot transfers, governance, staking, all of the stuff you do with dot tokens on Polkadot. We want to put that into a parachain itself, so that none of it is in the relay chain blocks. And then there's like a parachain for balance transfers, a parachain for governance, parachain for staking and whatnot. And then a relay chain block is just candidate receipts. Like there's nothing else in it except candidate receipts. All of the dot stuff is happening on like Polkadot parachains. So like Polkadot itself is a parachain of Polkadot, which is pretty cool. And that was it, yeah. Questions?
On the level of the collator, what are the mechanisms that we have to make sure that they're online for that parachain?
So it doesn't really matter, like...
Can you repeat the question?
Oh, yeah. So like the question is, for the collators, how do we guarantee that they're online, right?
Yes.
Yeah. So you don't really need to, like, you just need one collator to submit a block, and if they don't submit a block, then like this parachain has just missed a block, but there's no punishment or anything for them. So yeah, if you have collators who are offline frequently, then they're just, your parachain goes slower because it's not making blocks. But there's no like security risk to this at all.
So, yeah, that all happens in like 6 to 18 seconds.
Oh yeah, so that took me like a long time to talk about, but the plan is that from like actually like matching the collators and validators to actually and like doing all the checks and then like actually finalizing a block is about 1 minute, as long as there's no like invalidity reports.
And, okay, so the erasure coding thing, it seems pretty cool. Like, yeah, you can get like, split up this data into 100 chunks and I only need a third of that to reconstruct it. Why exactly? Like, what's the purpose of it? It seems like, I don't know, never looked into erasure coding before, but is it for like security reasons that like in case some of the network goes offline at this time, you can still reconstruct the data?
It's for
Or is it
the
for data efficiency?
it's for the availability guarantees. So like so that anybody in the net and for like the anti-collusion, so that like you know that these 10 validators haven't colluded with each other, so that like anybody else who's not one of the 10 validators can reconstruct this. So like Ethereum 2 will have like you know, like 1,000 validators on the shard, which is like an unreasonable amount to collude, but they don't have this like availability thing where like somebody on another shard could just request the state transitions for one of the other shards. So like in Polkadot, we just say like, well, we're gonna have like fewer validators, but we make it so that anybody can request this information at any time. Do you have a question?
Well, like, that's also what people use to solve like problems with privacy and anonymity. So they split it up and then like just route it in different directions.
Yeah, like shipping or secret sharing, or like a mixed net type thing.
Yeah.
Yeah, so like actually that's like a lot of this stuff gets pushed to the network layer, and like gossiping isn't really a great way of getting this information around. Like especially the erasure coding chunks where like they have an actual destination. So like it pushes like a lot of our data stuff not into the blocks, but it pushes it into the network. The stuff needs to get passed around. So that's like one of our next big push on the research and development front is like getting better networking primitives to like move this information around more efficiently without gossiping it. And mixed nets are definitely one thing that we're talking about.
What's mixed nuts? Is there like an analogy or something?
Oh, the
Yeah.
mixer. Like, so, like when people make transactions, you just split them up and mix them up together. Like you process like part of person A and part of person B and person C's transaction. But then like, the other parts are processed by some other node.
Okay, cool.
Yeah, it's like it'd be like an alternative to Tor. So instead
Yeah,
of
kind of like
running-
onion routing.
Yeah.
Onion router.
Yeah, that's true.
That sounds cool.
And then lightning is also trying to work on something like that.
Yeah, it's like parallel to the serial. Like Tor wraps things in layers and like you just like go, and this instead of like sending all the packets along the same path, you can have like a single layer mixed net, and you just send the packets to different relays.
Cool.
More? No? Okay, Gary?
Yep.